But I always wear a math shirt on Wednesdays. I try to anyway. This one is this one commemorates silence. This one commemorates the Voyager mission. Have I worn this before? Have I talked about this? So, quick story about that. Not that we have the time, but a mathematician solved the problem of trying to send out these Voyager probes in the 70s about using a slingshot method of slingshotting stuff around the planet to make it go faster and travel out deeper and faster into space. And then they came to find out that if they did not send the Voyager missions out in the 70s, whenever they were done, the next time they'd be able to do it, and I have it commemorated on the shirt, was in another 173 years. So when they went to President Nixon with their idea that, hey, we got to do this now, and then we can use the planets the way they're positioned are, we could see the whole solar system through these two probes. Or actually, they were thinking about one probe at first, and they go, and if we don't do it now, the next time we'll be able to do it is another 173 years. I'll put it in perspective. The last president that would have been able to do this and approve this is Thomas Jefferson. So basically, from Thomas Jefferson to Nixon, that would be the next time that they would be able to do it. So of course Nixon said, absolutely, we're going to do this, and then they decided to make two of them and send two of the probes out. So I wear that because it is a mathematician that solved the problem of how could we get those to travel fast out there. Okay, so I think these are on the worksheet itself. The only difference with this one is they're not equal to zero to start off. And I got to go fast. So I'm going to zoom in on this because we're on a shortened schedule. I'm not going to be here tomorrow. This is kind of like what you're going to run into tomorrow when you're working with your friends. First things first, all I got to do is do undo operations in order to get it equal to zero when you're dealing with quadratics. All right, quadratics, you don't do undo operations to directly solve for x. It doesn't work. This is not a linear equation. And then here's another thing. It does work out this way. Is that a fumble? that I want my leading coefficient to be positive. All right, it's actually easier to factor. I have a really hard time factoring when the leading coefficient fumble is not positive. Okay, are we doing that on purpose? All right. So I have a hard time factoring when the leading coefficient's not positive. So I would think many of you would as well. By the way, you always take out a what? 3, 2, 1, go. GCF. And then honestly, since this is an equation, you're not just factoring, you're solving by factoring. You can go ahead and never do this with a variable, but that 2 becomes meaningless because 0 divided by 2 is still 0. So it doesn't really factor into getting an answer. Careful! If you have to factor out an x, you don't divide by x to lose it. You actually have one solution, x equals 0, through the zero product property. Right, and then if you don't know how to factor this, I can't help you at this point. I'm done. I'm done with those that have troubles with their multiplications tables. That's not my problem. That's your grade school teacher's problem, and it's not their problem. You got to stop using your calculator and got to think about numbers more. He's so mean. Oh, by the way, speaking of mean, I also put some videos that might help you out from nice teachers. All right. So I put video 1 and video 2, some more help on solving by factoring. She's super nice. And she shows the 4-step method of factoring if you need it, and then verifies the zero product property. It's only like 5 minutes. And then another guy, you don't see his face at all, but he does more complicated factoring. And he literally says, there's many ways to do this, but really the best way is to just undo. You know, what I'm trying to get you to do, not the 4-step method, but just, unfoil and check. And he actually does a really good job of showing, what I've been showing you as well. But anyway, those are the answers. And now I can move on to this. Is there a 39 product property? Yes or no? 3, 2, 1, go. No, you probably don't know that. There's only a what product property? 3, 2, 1, go. 0. So this one you have to FOIL because I got to get this in nice 6x and I get a 4x is 2x. And then this is negative 24 and then that equals 39. Then I could subtract 39. So you feel like you're going in circles here by foiling. I have to, in order to, refactor and then use the zero product property. I mean, I could subtract 39, but then what do I do with the x minus 4x plus 6? You still got to multiply it out. All right, 30, 40, 59, 63, I believe. So this isn't today's. This really, I don't know if you needed me for this, but I figured this was supposed to be bell work after the fact, if we had our days in the right order. But I'm missing tomorrow, so. And then what multiplies a negative 63 and adds to 2? 7 and 9. Who's positive? 7 or 9 into factoring? 9. But then, see, this is where people get a little nuts here. They'll say, okay, the answers are 7 or negative 7 and 9. No, using the zero product property, it's the opposite of those. Okay, so be careful on that. All right, we got to move on. Vocab. Don't write any of this down. This is Mrs. Fasola. She loves the I can statements. I couldn't care less about the I can statements. I don't care that I'm on the record for that. I feel like you guys are going to walk out of Lockport going, I can't, because every teacher says, I can't. What can you do today? I can't. All right? I think you hear that all day long. Isn't that correct? Yes or no? Raise your hand if I'm right. Come on, raise your hand. All right, good. So we're kind of sick of hearing them. That's what Lockport does. They beat these things to death. All right? But anyway, we're going to be simplifying square roots, and we're going to talk about an imaginary number. What? What is that? If you come to think about it, all numbers come from our brain. But anyway, okay, so I showed this to you, I believe, yesterday in the notes or 2 days ago when did we have notes 2 days ago, I think? It's today, Wednesday. Where are we? What year is it? Is this 2022? All right, we've seen that some quadratic functions do not have x-intercepts. See that graph right here? Do you see it? Do you see that? Yes, well, say something. All right, and then what that means, though, for the first time in forever, Frozen, that you will have no real solutions for the quadratic. And then this is going to lead to what I'm going to teach Friday. And actually, it's talked about by the nice lady in the first video about what happens when you have a quadratic that doesn't hit the x-axis. Then she mentions the quadratic formula and then says, in my next video, I'll show you how to do that. And I haven't shown you that. But you can always search her and see that next video to get ready for Friday. So these solutions literally are called imaginary solutions. And we're going to introduce that imaginary thing. In addition, you don't have to write this down, not all quadratic functions are factorable, but they have real solutions. They're basically square root solutions. They're non-terminating, non-repeating decimals. That's an irrational number. So radical answers could occur. So that's why on Friday we're going to have to show you the quadratic formula. All right, and that's all I got to say about that. We got to move on. Oh, you guys drive me crazy if you don't know your times tables. All right, so look at that thing. You see it? You see it? You should print one of these empty until you got these down, because this is why you can't factor, maybe. This is why what we're going to do today is going to be a problem. So if you can't think about what times what equals a number, then it's over. Right? We're going to have no calculator on this kind of stuff, and you got to be numerate is what it is called. But I'll give you a minute to maybe write some popular squares, because this is what the notes are going to be, simplifying a square root. And we have to do this because the quadratic formula has a square root in it, and then you got to simplify it. So we got to spend a day of talking about simplifying radicals. Although in a later chapter, we are going to do radicals even more. Right now, we're going to do just the basics of simplifying, and then how do I do or deal with the square root of a negative. So I'm stalling. I'm going to zoom in on A, B, C, and D one at a time, two at a time. But these are perfect squares you should know, and I believe you should know 15 squared. I'm going to take it a little step further. All right, so a lot of these are obviously 1 through 12 squared. Those would exist on the that thing I showed you, the times tables. All right, and then you should definitely know 121 and 144. You should be able to go up to 12 squared. But I think you should go up to 15 squared. And then, what's 20 squared? That should be a really easy question. 3, 2, 1, go. 400, 400. What's 30 squared? 3, 2, 1, go. 900. What's 40 squared? 1600. You just add 2 zeros, and then so those are easy as well. Those should be no calculator scenarios. Anyone know 25 squared? That's another popular one. 3, 2, 1, go. Oh, nobody knows. 25 squared. 3, 2, 1, go. Oh no, nobody knows. 6. Anyone? 6. 625. That's not good. Not good. All right. So, first example. I get some crazy answers. I got people that are like robots. They just like, okay, this is what he said to do in class. Oh, I don't quite get it. That's my answer. And they're just trying to do a process that was shared in class. Really hope my microphone's on. I never know with this thing. So, what's the square root of 36? 3, 2, 1, go. 6. That's what a square root is. What number times itself equals 36? That's what that question says. But I get goofballs that double square root. They'll put the answer square root of 6. What are you doing? What's the square root of 36? 3, 2, 1, go. 6 free. No square root around it anymore. All right, these are the goofy things that I see. Let's move on. No time. 63. What times what equals 63? Listen to your friends. 3, 2, 1, go. 9 times 7. And if you cannot do that, that is a problem. And that is your problem and nobody else's. I can't help you. I cannot help you with this. Okay, these are base. This is like going into English class that you're like you have to write a composition. What's a noun? What's a verb? You don't know the basics, you can't write a composition. All right. And then, by the way, you can write this as a product. And this is where I get goofballs. The answers I get are just totally nonsensical. Let me ask you a simple question. What's the square root of 9? 3, 2, 1, go. 3. So, but I get people do this. They do this. They go 7 root 3. I have no idea what you're doing. I can't even answer this question about how someone switches who's in and who's out. One more time, what's the square root of 9? 3. So 3 is free, and root 7 is stuck, and you write it as a product, but you never have to write that times anymore. Okay, so I can break down square root of 63 and the square root of 9 times the square root of 7 separated, and then the square root of 9 is 3. I don't know what I can do to get this to not make those silly mistakes. 2 things about 108. 108 is even, so what goes into it? 3, 2, 1, go. 2. If you don't know that, get out. All right? And then I got something else. I know what else goes into 108 because 1, stop that. Put your hand on your own desk. Thank you. What is 1 plus 0 plus 8? 3, 2, 1, go. 9. Hey, so the digits add up to 9. You know what goes into 108 then? 9 itself. And that works for 9 and 3. Those two numbers. So 1 plus 0 plus 8 is 9. 3 goes into 9, so 3 goes into 108. But actually 9 goes into 108. But actually I'm going to go back to, well, you know what? I'm going to take a 9 out. All right, I knew the pen wasn't activating. All right, maybe you'd go to your calculator and say, okay, what's 108 divided by 9? And I think it's 12. Oh, wait a minute. What's 12? A number. But what is 12 as a product? 3, 2, 1, go. No one said 2 times 6. Thank you. Because 3 times 4 is better. Because who's a perfect square? 3, 2, 1, go. Now, this is what I'm going to do. I'm going to turn this back into this. What's 9 times 4? 3, 2, 1, go. Because that is a perfect 3, 2, 1, go square. Right? So you can do one way or the other. Notice I didn't tree it all the way out. Notice I didn't take 9 as 3 times 3, 4 as 2 times 2. No. I want to identify the biggest perfect square inside that radical. And then I could say, what's the square root of 36? Everyone, 3, 2, 1, go. 6 out, root 3 in. Because the square root of 36 is 6. That's why it's free. That's the evaluation of it. Don't know what happens. Oh, my seniors in CAT, I could see it's coming. You know, we just had a quiz on yesterday or the day before, and some are getting it, some are not. I don't know what they're doing in my class. They're licking the walls during the notes or something. They just don't pay attention or something. Drives me nuts. Hey, 4 plus 0 plus 5 equals what? 3, 2, 1, go. So guess what goes into 405? You know what else goes into 405? It ends in a 5, so what else? 3, 2, 1, go. 5. But I'm going to go ahead. I wonder if 5, you know what? I'm going to go back to that 5. I know, you want to know why? 5 times 80 is 400. So 5 times what is 405? 81. So 400 plus another 5, that means I needed one more 5. All right. So I can write this like this and then bring that 2 down. What's the square root of 81, everyone? 3, 2, 1, go. So 9 is out. And then this is how you have to write it, just slowing it down for the notes. Then it becomes 18 root 5. What time is it? Oof. Is it 24? Do I have that right? Wow, I can't believe I remembered the Wednesday schedule. All right, now we got exercise 2 or section 2, and then a whole bunch of examples after that. I'll fit as many as possible. And now you got to speed this up. But you got to know right now that the square root of negative 4 is not possible, just as an example. What number times itself equals negative 4? Well, what's negative 2 times negative 2? 3, 2, 1, go. 4. You can't say 2 times negative 2 because those are not the same number. So you can't get two numbers multiplied together that equal a negative. So this is what somebody, I should look it up, who made this stuff up? Who made up this imaginary number thing? And by the way, imaginary numbers, the electricity in this room exists because of imaginary numbers. That is actually a truthful thing. I numbers actually are very practical and useful in electronical engineering. All right, so just some things like why do I care about this? All right, there's at least one thing. So some person said, you know what? Let's separate this. Let's get rid of that negative as a separate square roots. And then you know what? Let's call it something special. Let's call it like a particular letter. And then someone said, how about I? And everyone else is like, that sounds great. I really don't know what else to tell you. This is the truth. So from here on out, you must know that the letter I, when you see it in the stuff that we're doing right now, that equals the square root of negative 1. It is not a variable. A variable means, the word definition of variable means changing. Right? That's why x, every day, is x equals something different when you're solving. It's a variable. I is not. I actually represents the square root of negative 1. And then what the people can do now is, okay, what's the square root of 4, everyone? 3, 2, 1, go. 2. So literally, the square root of negative 4 can now be evaluated as 2i. All right? And then believe me, there's I applications that are very important in the world that we live in. So I equals the square root of negative 1. And then I have a weird set of questions for you. Just humor me. What's the square root of 2 times the square root of 2? What do you think that answer is? 3, 2, 1, go. Oh, nobody knows. Square root of 4, which is what? What's the square root of 4? Oh my gosh. 2. Okay, so let's get a little faster here. What's the square root of 7 times the square root of 7? 3, 2, 1, go. What's the square root of 23 times the square root of 23? 3, 2, 1, go. 23. So what is I squared? Careful. It is not 1 because you cannot take a negative times a negative underneath a radical. So underneath all those things that I said there, what do you think the square root of negative 1 times the square root of negative 1 is? 3, 2, 1, go. Negative 1. And then this is where goofiness happens again. Is negative 1 the same thing as the square root of negative 1? What would you rather have, $100 or the square root of $100? $100, because there's a difference. So don't ever tell me I is negative 1. No, I is the square root of negative 1. I squared is a free negative 1. These are two completely different things. And these are the things that you need to know about an I number. Okay? And it gets crazier from here, but I'll wait because we don't have time. What's I to the 5th? What's I to the 4th? You can do those evaluations, but no time. So, square root of negative 25. Write it down real quick. Okay, done. This is the square root of negative 1 times the square root of 25. What is this final answer? 3, 2, 1, go. 5i. And that's how you want to write it. That is exactly how you want to write it. It's a Federmact on your graphing calculator. I think you have to be in imaginary mode, so don't try it. You can type that in your calculator and it'll spit out 5i on your calculator. But you have to be in imaginary mode. Oh no! What's 26? What times what? 3, 2, 1, go. Are any of these perfect squares? So guess what you're stuck with? Usually I like writing the I out in front of a radical. So there's nothing to simplify, but you could, and I think certain books do write it like this. Just make sure it's not underneath the radical for the 26. But I like writing it I root 26, and I probably always will. There's no hard rule on which side you write it on. Okay, next one. What's 27? What times what? 3, 2, 1, go. 9 and 3, I heard. I heard someone else say something that was not. Actually, I don't think there could be any other product. Okay, so forget it. I thought I heard something weird. Okay, so what's the square root of 9? 3, 2, 1, go. 3. What's the square root of negative 1? 3, 2, 1, go. I. And then root 3 is stuck in there. This is how I like writing it. And by the way, these are all products, so multiplication's commutative. I can move things around in order. So again, you can put the I in the middle or the I. Is everything okay? Okay. What is 162 divisible by? 3, 2, 1, go. 2. It's also divisible by 1 plus 6 plus 2, 9. So actually, I'm gonna search out that 9. So don't forget we have a 2 out there, and then don't forget you got a square root of negative 1. Take out an I like to say, and then this is square root of 9, and then I might want to go to my calculator and see what's left over there. Ooh, I don't know. So 9 times 15, 45. 16 is 7, 9 times 7. I don't know. How many times does 9 go to 162? Is it 18? Okay, wait a minute. Oh, I'm a fool. I'm going to erase this. I'm going to take out a 2 because what's 162? 2 times what? Because I heard 18. I know there was another 9 in there. So I knew there was an 81 in there. So again, notice how I erased. I erased and went back and said, okay, 9 times what equals 162? 18. Wait, 18 has another 9 in it. 9 times 2. So then I went backwards and said, all right, it's 2 times 81. And get those two 9s together. What's the square root of 81? 3, 2, 1, go. What's the square root of negative 1? 3, 2, 1, go. All right, so 2. Don't forget about that. 9. I stuck in jail. Root 2. That one did not get to simplify. I don't understand why people make radicals difficult. It's going to make a comment about that. It's not. You get it structured. You know why it is? Here. This is why. That. It's your fault. Nobody else's. He's so mean. I don't care. All right. Next. 216. Ooh, 26. Oh my gosh. 6, 1, 2. What goes into 216 yet again? 9. So let's see what's left over. So here we got negative 4. We got times square root of negative 1 to isolate that. And then I know at least a 9, but I may erase this. Did anyone find out how many times 9 goes into 216? 24. Okay, I'm going to have to do something with 24. What is 24? A number. What is 24? What times what? 3, 2, 1, go. 6 and 4, but 8 and 3. Which one's better? 6, 4, 8 and 3. Which one? 6 and 4. Okay, now this is what I'm going to do. These are all still underneath a radical. But I see these two perfect squares. What's 9 times 4? So I just like doing this. Okay, one more step. I'll write that as square root of 36 and then stuck with 6 in jail. Let me double check that 36 times 6 is 216 still. It is. And then everyone, what's the square root of 36? 6. You could also do the square root of 9 is 3 And the square root of 4 is 2, but you brought a 2 and a 3 out, that's 6 brought out. So it's the same thing. You can't do this wrong as long as you're solid with the math. All right, unfortunately, I got a 6 out here. That's an I, and I got a 6 in there. That's still stuck in jail. Final answer is negative 24I root 6. What time we got here? Okay, we're running out of time. All right, so I got to do, well, I'm going to go to that last one. We're going to skip C here. Maybe when you leave, I'll do C as you're walking out the door. Oh, no. 8 plus 2 is 10. 9 doesn't go into this. But at least 2 does. So this is what I'm going to do. I'm going to do the full tree on this. 2 times. I think I can get this one, 104. Well, 104 is 2 times 52. 2 times. Is that 26? 2 times 13. What's 2 times 2 times 2 times 2? 3, 2, 1, go. Oh my gosh, I'm going to throw a podium. What's 2 times 2 times 2 times 2? 16. Okay, so 2I root 16 root 13. So I took out an I. Oh no, I already had an I. My bad, dogs. Roof. Okay, so I got to move this over. I also have the square root of negative 1 here. Okay, so I almost forgot that because I had another I. I almost lost an I. Ooh, that sounds terrible. Okay, now, so this is 2I times I, which is I squared. And then the square root of 16 is 4 out here. And then I got root 13 stuck in jail. Okay, might have to do all of these after the bell. What is I squared? I just told you this in the notes up there. 3, 2, 1, go. Negative 1. So now this is 8 times a free negative 1, root 13. So now it's negative 8 root 13. No I number exists anymore. I squared is a free negative 1. Okay, so I broke that down as much as possible. As you're packing up your stuff, okay, this actually is, anyone recognize this? This is what the quadratic formula looks like when you have to use it. So at the end, as you pack up your not backpacks, PEMDAS. What's P stand for as you put your stuff away? Parentheses. I don't really have that, but really what it is it's grouping symbols. So I have to take care of that grouping symbol. And then within that, I have an exponent. I swear to dog, you people that press this on your calculator, negative 3 squared, enter, and you get negative 9 and write it, you're killing me. That's positive 9, and negative times a negative. And then MD, multiply, 4 times 5, 20 times 2, 40. I'm still not done with the grouping symbol. So now I have to take 9 minus 40. I can do 2 times 5. Nobody's like, listen to them. They're just all running out of here. And then 3 minus, I got to finish this whole 9 minus, good thing 9 minus 40 is negative 31, because this is not, doesn't reduce. When I do the quadratic formula on Friday, we'll have ones that simplify even more. But what you got to do, have a good day. See ya. Is take out an I. And then you're left with this. Okay, so simplifying a radical with numerous operations, that's what the quadratic formula is going to look like. And then this one's simple. PEMDAS, exponents first within the grouping symbol. And then negative times a negative is a positive. So you feel free to do that. 4 to 2 is 8. And then 8 times 3 is 24. And this is still underneath the square root. And then no, you can't take these separate square roots. You have to add first. That's 60. Then what's 60? 6 times 10. 6 has a 2. 10 has a 2. So 4. 4 times 15. Notice there's no i's in this. There's no square root of a negative. So Square root of 4 is 2. This is just 2 root 15. That's all she wrote. Where are we at? There we go.